Hi. So it's time to learn a little bit about how to write chemical equations and balance them. The process is pretty straightforward if you have the pieces in place. And one of those major pieces is being able to write formulas. To start with, a chemical equation is a representation. It's a way of giving a whole bunch of information about a chemical reaction using chemical formulas and symbols. Now, formulas we already know. We know how to write formulas. Okay? Symbols are a little new, but there are not very many of them, and they're pretty straightforward. So what's important about a chemical reaction equation, if you've written it carefully and correctly enough, is that it's not only going to tell you what substances are involved in the reaction, but it's going to tell you how much of each substance is necessary for the reaction to occur. Okay, so it gives the most important information about a chemical reaction. So the first step in this process is going to be to write skeletal equations. So like a skeleton is the bare bones of a person, a skeletal equation is the bare bones of the reaction, just the substances involved and some information about their physical state. So we're going to have names of substances, and we're going to need to translate those into formulas. We've done this already. Ionic compounds, you know how to write your ionic compounds. Get the formulas for both ions, do the crisscross method, and reduce. Okay, acids. You want to go back and watch that video again about how to name common acids. It's going to be very important here. Molecular compounds, using prefixes, right, and writing a formula based on that. And then any element from the periodic table, including the 7 diatomic elements: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Remember that those are written as twos, diatomic, 2 atoms of each element. Okay, so make sure you know those. We're going to use state symbols to indicate what physical state each substance is in. So we use a little s in parentheses if the substance is a solid. We'll use an L if it's a liquid. We'll use a G if it's a gas. And the fourth one is AQ. And AQ is used if the substance in question is dissolved in water. We call that an aqueous solution. The word aqueous has at its root the word for water. Okay, so aqueous means dissolved in water. It's a solution. Between the starting materials, the stuff that we put together before the reaction occurs, and the ending materials, the stuff that's produced, we have an arrow. We don't use an equal sign, even though it's called an equation. And in math, an equation is anything, a sentence, a mathematical sentence that contains an equal sign. Well, we don't use an equal sign because an equal sign means that one thing is equal to the same as another. But in chemistry, we know that in a chemical reaction, things change. And so the arrow is there to indicate that there's a change happening. Okay, so here's an example, and we're going to take a look at this. A piece of aluminum metal is placed into a solution of copper 2 chloride, producing solid copper metal and a solution of aluminum chloride. This is the first chemical reaction you observed, well, the second one. First was the gummy bear, but this is the first one that you actually really did. You took some aluminum foil, you put it into that solution of copper chloride, and you watched it smoke and bubble, and you saw what looked like rust, and we talked about all of that. Well, that was the copper forming, and the other solution was the aluminum chloride. So let's write a skeletal equation for this reaction. So to start with, we need to translate aluminum metal. That's just Al. And because it's a metal, most metals, almost all of them, are solid, so I put a little s in parentheses down here next to it. A solution of copper 2 chloride, so now I need to write my formula for copper 2 chloride. Copper is plus 2, Cl minus, so Cu, Cl2. And that's a solution, it tells me in the problem, so I'm going to put aqueous, Aq, down there. That's what I mixed together. What came out of the reaction, there's my arrow, was solid copper metal, Cu, with a solid, and a solution of aluminum chloride. Al is plus 3, Cl is still minus 1, so it would be AlCl3, and that is a solution, so aqueous. So there's my skeleton for that reaction. This tells me what substances are involved and what physical state they're in. Now, there are some things that are not quite right about this equation the way it's written. If you look really closely, you'll see that on one side of the equation there are 2 chlorines, and on the other side there are 3. That's a problem that we're going to have to fix. The reason that's a problem is because of something called the law of conservation of mass, which says that in any chemical or physical change, matter can be neither created nor destroyed, but must be conserved. And in that example that we just did, the number of chlorines were not the same on both sides, which means we suddenly seem to have created a chlorine atom out of nowhere, and that's not allowed. So what do? Well, we balance the equation. And balancing is a way to make the equation adhere to the law of conservation of mass. You have to have the same number of atoms of each element on both sides of the equation. Okay? Now, I can't change my formulas to make this happen. Okay? I can't make copper 2 chloride CuCl3 because that's not the formula for copper 2 chloride. What I can do is I can use something called a coefficient. Now in math, you've heard the word coefficient. It's the number multiplied by a variable. In chemistry, it's the number technically multiplied by a formula. It goes in front of a formula, and it's used the same way it's used in math. It multiplies everything in that formula. Okay? All the atoms in a formula are affected by the coefficient in front of it. It's a large number that comes in front of a formula, and you've probably seen them before. Okay? When I'm done putting my coefficients in, they should be in the lowest whole number ratio to one another. If they're not, you reduce them all together by a common factor. Okay? So let's go back to our balanced or unbalanced skeletal equation, and let's balance it. Okay? On this side of the equation, which, by the way, this side of the equation is called the reactants, the things that are reacting. And this side of the equation is called the products. Okay? So the reactants are aluminum and copper 2 chloride. The products are copper and aluminum chloride. We need to make sure we have the same number of atoms of each type on both sides. Now the aluminum, there's one atom of aluminum here and one here, so that's okay. And there's one atom of copper here and one atom here, and that's okay. But there are 2 atoms of chlorine and 3 atoms of chlorine over here. And that's a problem. We have to make the chlorines equal. And the only way I can do that is by putting a number in front of these 2 formulas that will get me the right number of chlorines on both sides. The trick here is to use the least common multiple. Okay? Least common multiple of 2 and 3 is 6. So in order to get 6 chlorines on this side, I'm going to need to put a 3 in front of that. That gives me 3 times the 2 chlorines that are already there. That's 6. In order to get 6 chlorines on this side, I have to put a 2 in front of that one. That's 2 times the 3 chlorines that are already there. Now the problem is my chlorines are fine now, but now I've messed up my copper and my aluminum, so I have to fix those. I now have 3 copper atoms on this side, so I'm going to need to put a 3 in front of the copper there. And I now have 2 aluminum atoms on the product side. I'm going to have to put a 2 here. Are these in lowest whole number ratio? Yes, they are. 2 to 3 to 3 to 2. I cannot reduce it anymore. So this is now a balanced chemical equation. So here are some tricks to help you. Okay? If you have polyatomic ions in your formulas, and the same polyatomic ion shows up on both sides of the equation, you get to treat that as a single unit. That's going to make your balancing a lot easier. You don't have to, but you can. If you get stuck and it's not working, try doubling the coefficients you've already placed. Almost always will fix things for you. And finally, we already talked about using the least common multiples to find coefficients for tricky atoms. Okay? Let's try another example. We have solutions of lead 2 nitrate and potassium iodide. We're mixing those together. We're going to produce something called solid lead 2 iodide, which is a precipitate. Precipitate is a solid, and a solution of potassium nitrate. Okay? So let's see what this is going to look like. We'll write the skeletal equation first, and then we'll balance it. So, our skeletal equation, we need lead 2 nitrate. Lead is +2, nitrate is -1. So lead 2 nitrate would be Pb parentheses NO3 2. And that is a solution, aqueous. Potassium iodide, K plus, iodide is I minus, so that's just Ki. And that is also aqueous. Solid lead 2 iodide precipitate. Lead is +2 in lead 2, iodide is -1, So that is PbI2, and that is a solid. And potassium nitrate, which is a solution. Potassium is +1, nitrate is -1, so that's just KNO3, and that is aqueous because it's a solution. Now, this is our skeletal equation, but it's not balanced. If you look carefully, you'll see that there's only one iodine here, and there's 2 iodines there. There's only 1 nitrate here, and there's 2 of them here. So let's balance it. We have 1 lead on both sides, so the lead is fine. This is a polyatomic ion, nitrate, and it shows up on both sides of the equation. There it is there, and here it is over here. If it shows up on both sides of the equation, I don't have to think of this as 2 times 3, 6 oxygens and 2 nitrogens, and over here 3 oxygens. All I can consider this is 2 nitrates. There are 2 nitrates on this side. There's only 1 nitrate over here. So if I put a 2 in front of KNO3, the 2 multiplies by the whole NO3, and it gives me 2 of them, which matches the 2 that are over here on the reactant side. By doing that, though, I've also added 2 potassiums to this side, and there's only 1 over here. So I'm going to put a 2 in front of the potassium iodide to give me 2 potassiums. That also gives me 2 iodines, but that's okay because I need 2 iodines over here. Now I check. My coefficient here is a 1. I don't need to write in a 1. If it's just a 1, you leave it, but it's a 1, and a 2, and a 1, and a 2. 1 to 2, 1 to 2. That's balanced, and it's in lowest whole number form. So there's your balanced equation for this reaction. A lot of information in that. Now you try. I want you to write a balanced chemical equation for this reaction. A piece of zinc metal placed into a sulfuric acid solution producing hydrogen gas and a solution of zinc sulfate. Stop the video and see if you can translate this into chemical formulas and symbols. Got it? Well, let's see how you did. Zinc metal, that's just Zn solid. Sulfuric acid comes from sulfate. That's H2SO4, and that is aqueous. Sulfuric acid solution. Producing hydrogen gas. Hydrogen is not just H. Hydrogen is one of the diatomics. It needs to be H2 always when it's by itself, and that is a gas, G. And a solution of zinc sulfate. Zinc is a +2 ion. Sulfate is a -2 ion. So zinc sulfate is just ZnSO4, and that, according to the description, was aqueous. It was a solution. There's my skeleton. Let's see about balancing it. I have 1 zinc and 1 zinc. Great. I have 2 hydrogens and 2 hydrogens. I have 1 sulfate and 1 sulfate. It's already balanced. Sometimes you get lucky. Sometimes you don't. So that's really all there is to it. Writing formulas is probably the most important part of this, and then balancing will be second. But if your formula is not written correctly, you're never going to be able to balance these things. We're going to get lots of practice. Make sure you ask questions in class.